In this video, we're going to apply the rule that we generated in the last example, where we said if we have 1 over x minus 1 as a single linear term, but x plus 2 all squared as another term, then the partial fraction decomposition has to work like a constant over the linear term. Then we need an x plus 2 all squared. But we can't just have that if it's squared. We also need the x plus 2 to the single power. And we're going to build up a collection of terms that go with that. That would be the partial fraction decomposition that we're looking for. And away we go. We do our usual thing of getting the common denominator. And for this time, I'm just going to show only the numerator, because we know at this stage how to manipulate polynomials. And if the denominators are going to be the same anyway, why write them out? So on the left-hand side, we have a 1. On the right-hand side, we have a over x minus 1, but it's missing an x plus 2 squared, so we would have to multiply it top and bottom by x plus 2 squared. Then b is over x plus 2. It's missing an x minus 1, and it's missing another, or the second x plus 2, whereas c has both x plus 2's that we need, but it's missing the x minus 1. So we can very quickly arrive at the equation that governs this, and this has to be equal for all x's. That means either at individual values or the coefficients of the x's on either side. So just a quick reminder, this is a quadratic on top, x here, that's all we got, quadratics. So implicitly, even though we can't see it, we have 0 x's and 0 x squareds on the left-hand side. We could change the question easily enough and have this be x squared up top, then that term would exist or be non-zero and be more interesting. But if we have a simple 1, we just treat those missing coefficients as zeros. So we're going to use our shortcut again, because again there's low-hanging fruit. We're going to let x equal, two nice values would be x equals 1. Let's start with that one. That'll give us 1 on the left-hand side, and 1 plus 2 is 3, so it'll be a times 3 squared, and b times 0, and c times 0. And that should be a plus. And so we quickly get that a is equal to 1 over 9. Lovely. There's another possible value that's going to simplify this equation, and that would be negative 2 for x. And if we sub that in, the left-hand side of our equation stays at 1, because these x's don't appear. Then for each of the other terms, we get a times minus 2 plus 2 is 0, b minus 2 plus 2 is 0, and then c is where it gets interesting. We'll have c times minus 2 minus 1 times negative 3. And so c is going to be, these terms both go away, we're going to have c is negative 1/3. Perfect. Now we're pretty much out of the shortcuts, so we're going to go back to the fundamentals. And that's where we set or note that these two equations are completely equal to each other for all values of x, which means the coefficients of x and x squared and the constants have to be the same. So we equate the coefficients. We will do that on the next page though, because we will need to expand these guys out before we can actually work with them. So let's carry this whole equation to the next page and see what we can do with it. Expanding the right-hand side is going to be a times x squared plus 4x plus 4, and b times x squared minus plus 2 plus an x minus 2, and then c times x minus 1. And a reminder that a is equal to 1/9 and c is equal to negative 1/3. All right, now we can pick any of the coefficients that we like, because I think they all involve a, b, and c. Let's look at b. We have a bx squared, so let's look at the quadratic coefficients. So coefficients of x squared. On the left-hand side, we have 0 x squareds. On the right-hand side, we have, think about all the ways we can get an x squared. It'll be an a times an x squared, a b times an x squared, and there are no terms with a cx squared, so we just get a plus b. If we expanded all of this out, we would get a plus b times x squared plus a bunch of other stuff, but that'll be the only coefficient for the x squared terms. And if that's the case, well, that means that b is equal to minus a, but a equals 1/9, so this is going to be negative 1/9 for b. And we've now found all of our a, b's, and c's. The last thing to do is remind ourselves, how did we assign those to the different denominators? The order doesn't matter here, so you have to go back to how you set it up. But here we have a over x minus 1, b over x plus 2. So our integral of 1 over x minus 1 times x plus 2 all squared has to equal the integral of a, 1/9, times or over the x minus 1 factor. And then we had the negative 1/9 over or times the 1 over x plus 2 linear factor. Then last but not least, we had c, which was negative 1/3, times the x plus 2 in the denominator squared, and all of that with respect to x. And why is that easier than the original integral? Well, because each of these terms separately now can be integrated on their own. So we're going to end up with 1/9 ln of x minus 1, absolute values, minus 1/9 times ln of x plus 2, and minus 1/3. And again, remembering that this whole expression is x plus 2 to the negative 2. We integrate, we get one higher power, will be x plus 2 to the negative 1, which is the same as 1 over x plus 2. But we divide by the new power, which is negative 1, so we get a double negative going on there. And plus a constant we haven't used in this problem, so d. And if we wanted to, we could just do one last tidying up stage. Minus 1/9 ln of x plus 2's, and then plus 1/3. 1 over x plus 2 plus some arbitrary constant. Now, as a quick wrap up, there are two more cases that we haven't covered, and that's where we have quadratic factors. Again, there's some nice theory that says no matter what polynomial you start with, it can always be decomposed to linear or quadratic terms, quadratic factors, and you'll always be able to break it down to that level using real numbers. For this course, it'll be sufficient to have the linear examples covered. The quadratic you'll see in later courses. And the note that goes with that is partial fractions is a tool that it just seems like one more element of the toolkit for integration at this stage. Totally fair, and that's all it is so far. But it will come back in quite a substantial way. And again, there's some fun theory that we can't cover here, tying Laplace transform. So this is a thing that gets used in a differential equation class, math and engineering 225, 231, 237. I'm missing some of the ones in the Queen's catalog, but every student in engineering at Queen's is going to take a differential equation course in second year. It will have Laplace transforms, and you will be doing partial fractions with them. So we're laying some groundwork here in the context of integration, but in practice, you'll see it in a different light in your second year differential equation classes, and further on from there for those who go into control theory.